Hello everyone, it's been a long time since I made a video, so bear with me while I get my feet wet again on this. So we're looking at binomial and geometric probability models. Both of these use what are called Bernoulli trials. In a Bernoulli trial, you have three requirements. Two possible outcomes. Oddly enough, we just call them success and fail. And sometimes it might mean success equals getting a disease and fail means not getting it. It's kind of weird that way. The probability of success is constant, and then also trials are independent. So like if you had a regular deck of cards, you're pulling cards out and you were saying spades versus not spades, that would not be a Bernoulli trial because your trials wouldn't be independent unless you have an infinite deck of cards like we will have in a moment. So geometric probability models are when you count the number of trials until success. So you count until you see the spade you want to see. I'm going to keep talking about spades for cards. It'll just be our example for this whole video. So you might go like heart, diamond, and then you see your spade. And so it took you 3 trials until you saw that success. Now, a binomial probability model is when you count your number of successes in n trials. So you'd be counting how many spades in a deal of 10 cards. Okay, so let's look at some examples. So with our infinite deck of cards, that way we can have that constant success thing. Success is going to be drawing a spade, fail is not drawing a spade, so that means our success, our probability is 0.25, and then our fail, that's just 1 minus our probability of success. Our textbook calls it Q, but 0.75. So as an example, say you're drawing cards and you want to know the probability of drawing a spade on the 5th try. So if you're going for a spade on the 5th try, that would mean you would have to fail, 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 succeed. Hooray! And so multiplying through, you get on that 81 out of 1024 or 0.079. So if you think about it, like, not getting a spade until your 5th card, that's not a really weird deal of the deck. It's not super common, but not crazy either. So, and again, this is with an infinite deck. Now, this is kind of annoying. I mean, I could do 3/4 to the 4th here, of course, but our calculator is really kind of smart about these things. So this is a geometric probability model because we're counting the number of trials until success. If we go to our calculator and we go into the distribution menu, we know that menu well because of normal CDF and INV norm, hit the up arrow and you can see 2 things here. There's Geomet PDF, Geomet CDF. And the Geomet PDF is what we'll want this time. So the PDF means that it probably stands for something official, but I think of it as perfectly the number you want versus count your way up to the one you want. So like here, draw a spade by the 5th try, so you could get your spade 1st, 2nd, 3rd, or 4th, 5th try kind of thing. So we want this Geomet PDF. We'll go in here, and then it asks for a P, our probability, 0.25, our X value, that's our trial number. And then just like when we're doing normal CDF, the thing we write matters. So what we write is that Geomet PDF on our calculator. And then we have this list here, so we can write P equals 0.25. And then I like to write success here, like as in I'm getting success on the 5th try. You can also write an X there. And if we do that, we get 0.079. It's the exact same number as before, which is good. So that's an example of getting like exactly a success on the 5th try versus getting a spade by the 5th try. So that would be, 1st try, 2nd try, 3rd try, and so on. We could do this by hand. It's great. It's really fun, I promise. You could be successful on your 1st card. Woohoo! Or you could go, no spade followed by a spade. Or no spade, no spade, spade. And then again, I could draw 3 in a row followed by a spade, and then 4 in a row followed by a spade. I'm not writing those out to save some time. And if we throw that whole thing into our calculator, which do you really want to do that? Probably not. We get 0.763. Oh, seriously, the pen's dying? Great. Fine, I'm switching. So 0.763. So this was, you know, it's cumbersome enough with 5th try, but would you want to have to do that for the 10th try? Probably not. So we go back into that second distribution, and then we arrow up again and choose that geomet, this time CDF, as in we're counting our way up. It looks just the same as before. We put the 0.25 in, we put the 5 in, we write down geomet CDF, and then P is 0.25. I can either write success or I can write X. We have a 5 there, and I paste that, and I get 0.763, which is what I had before, of course. So it makes good sense that you are far more likely to get your spade on or before the 5th try than on the 5th try, right? It's good that that makes sense. Okay, so this is again the geometric probability model, and this was the PDF, as in perfectly that out, you know, on the 5th try versus count your way up to the 5th try. And then also part of the geometric probability model, we can find means and standard deviations. So how many cards would you expect to draw before you have a spade? Now, our handy formula sheet, if you look to the probability page, we can look for the word geometric, and then there's mean 1 over P, standard deviation, square root of 1 minus P over P. So this is really nice. We don't have to memorize these two formulas. They're on our formula sheet. Note that that first formula I did, that on the very first example, that formula is here as well. But we don't need to do it by hand. So again, out to get, so that when you see that word expect, that really means the mean. So the mean of our X was 1 divided by P. 1 divided by a 4th is 4. And if you think about it, wouldn't you expect it to be like the 4th try for getting your that 4th suit? I don't know, it just seems it feels good to me. Just like rolling a die, like the expected number of rolls to roll, say, a 6 would be 1 over a 6th, being 6. Kind of cool. And then our standard deviation is that square root of 1 minus P over P. Our textbook, by the way, does this as Q over P squared square rooted. That's exactly the same thing. Just I'm giving it, I like the formula sheet way better, just partly because it's on the formula sheet. So our standard deviation is going to be 1 minus a quarter square rooted divided by a quarter. So the square root of 3/4. Make sure you get out of that square root before you hit your divide. Divide by a quarter, and we get 3.464. So 3.5. This also, to me, makes good sense, because like if you're trying to get a spade, you might get it your first try. That's the soonest you can get it. You know, you would expect to take the 4th try. So 1 is about a standard deviation below your mean. And so it just kind of fits together. So this is everything we need to know for, again, this is the geometric. So be able to find something on the nth whatever try up to that number of tries, and then also your expected value, aka your mean, also your standard deviation. So that's our geometric. Now the binomial is when you're looking at, that's going to be on the next page, count the number of successes in n trials. So that's next. So like if we're saying, what's the probability of drawing 3 spades out of 6 cards? So this, it gets pretty complicated, quite frankly. And there is the formula sheet for it. It's right here. And it basically is saying, I just hate it. I'm not even going there. It gets really complicated because it's like you're talking about getting 3 spades out of 6. You might have your spades be the first 3, or it could be the third, the first, and the fourth, or whatever. So it's awful. I don't like doing it that way. I just like to recognize, like, yes, this is Bernoulli because, yes, we have 2 possible outcomes. We have our constant probability of success. We have our independent trials. So I know this, and it's the, number of successes out of n trials. And also, like, knowing that, we have this 3, we have this 6, we still have our probability of a quarter. So we have 3 numbers that we're working with. If you went into Geomet, PDF or CDF, there's only 2 numbers to plug in, so you'd be stuck. So this is binomial. And so we're going to use the binomial. We'll go back into our distribution menu, second vars, arrow up again. We have to go a little further. So, and the PDF, CDF, just like before, that PDF is perfectly the number of trials. So we have 6 trials, probability of success being a quarter. Our X value is 3. What we write is binom PDF. We write trials equals 6. Our probability a quarter. We could say X, we can say successes. I like success better. And then we can hit paste on that. And it shows up on our screen this way, but just like when you're using normal CDF, you label those numbers, you do that here too. And we get 0.132. And if you think about it, you wouldn't necessarily expect 3 cards out of 6 to be spades. That seems kind of unusual, which 13% is fairly unusual. Okay. Now, so that's our binomial PDF. And again, it's that number of successes out of a certain number of trials, still constant successes. So now we're saying probability of draw up to 3 spades. So you could have no spades, 1 spade, 2 spades, or 3 spades. So anything but 4, 5, or 6 spades, right? So going back in here, again, this is still binomial. And this time, though, because we're counting our way up to that 3, we will do the second vars again. We will do a binomial CDF, trials 6, probability a quarter, X value 3. Before I hit enter here, I like to write all this down. So binomial CDF, trials 6, probability a quarter, X is 3, and then I'll hit paste and I get 0.96, which that to me feels quite reasonable. Probabilities, remember, you can leave them as a decimal or fraction or a percent, however you like it, whatever you want. So there we go. Okay. Now, what if you wanted to know the probability of drawing at least 3? We've talked about at least in class. And when you see at least, I hope you say, aha, you can't fool me. Because when you see probability of at least 3, that's going to be do the opposite and subtract from 1. So 1 minus the probability of draw up to 2 out of 6. Yes? So you have to think through that really carefully and pay close attention. But now when you see this up to 2, that's just like what we did before. So we'll have that 1 minus the binomial. That'll be a CDF again. It'll still be 6 trials. Probability of a quarter. This time our X will be 2. I'm just going to do that and change that to a 2. And I get 0.83, so it's 1 minus the 0.831. So 1 minus that is 0.169. I'm too lazy to retype 1 minus those other numbers, so that's what we have. So, because getting at least 3 spades out of 6, that doesn't sound as likely, does it? Okay, so with the binomial stuff, we can use that binomial PDF, binomial CDF. That's perfectly the number in questions. The CDF is count your way up to it. And then with those at leasts, and this applies to geometric as well, you can do that 1 minus the opposite thing. And just like geometric, we can do expected value and standard deviation. So when you see that expect, we mean the mean. And once again, our handy dandy formula sheet, if we look at this in our probability section, we look for the word binomial, mean, standard deviation. So our mean is startlingly easy, even if it's difficult to say that. So it's just n times p, which makes good sense too. So 6 times a quarter, you would expect a fourth of your cards to be spades. So a fourth of 6 is 1.5. Now, it's okay to not have a whole number of cards here because it's a mean. For our standard deviation, that one is, our book says NPQ square rooted. The formula sheet says NP1 minus P square rooted. Either way you slice it, it's going to be 6 times a quarter times 3/4 square rooted. And if you chuck that in your calculator, you get something. 0.6 times 0.25 times 0.75, 1.06. So there's our standard deviation, 1.061. So there's this again for binomial, our mean, our standard deviation. And again, just a reminder, I said this earlier, but here it is in print, our memory device for PDF versus CDF. PDF, perfectly the number in question, versus CDF, count your way up to the number in question. And there is our fascinating, not really, tour of Bernoulli trials and binomial and geometric probability models.